Hello, everyone. Welcome back. And welcome to the Causality session, the most fun session of UAI 2024. And hope you are well fed, hydrated, caffeinated, and all ready for the fun session today. Our first speaker is Alexis Bellot. He's from Google DeepMind. Please come up and let's hear from him.
Hello, everyone. Thank you for having me. So I work on bounding because, at least in my view, most interesting questions are actually fundamentally underdetermined by the current state of knowledge, meaning that there really isn't a single ground truth for you to estimate, but often multiple compatible options that, if you wanted to characterize your problem correctly, you'd need to consider. And what's going to be a little bit different about my take on this problem is that I want to be a little bit more data-driven. So I don't want to make strong assumptions about having access to a causal diagram or knowledge of the structure of the functional relationships in your system or anything like that. I want to operate purely based on the observational distribution of your data and the independencies that it entails. So ultimately, the kind of thing that I'm after is to develop a program that takes your observations of your system and tells you as much as possible about the effects of interventions you might want to understand. At a high level, that's what I'll try to talk about. So to formalize this in a little bit more detail, you can imagine that you want to reason about a set of variables, right? These are some attributes of your system, some determinables of some sorts, measurements, right? And when you merely observe the value of these systems when they're caused in the normal way, right? The information you get about a variable also tells you something about its causes, the effects of those causes, and all the statistical relationships that are involved, right? All this is encoded in what's called an observational distribution, right? And but this is a little bit different than if you want to reason about your system under an intervention. So now imagine that as an external actor, you go and you set the value of a particular variable to some number. Here, you're overriding really the underlying causal mechanisms and potentially completely changing the dynamics of your system and creating maybe a very different set of downstream events. Right? So this contrast between this contrast between observations and interventions was known, or at least began to be understood in statistics, at least since the work of the biologist and statistician Cyril Wright in the 1920s. And actually, the contrast between interventions and observations has very deep and wide-ranging consequences. In fact, it has been showed on the different versions that you can almost never infer the value of interventional probabilities only with knowledge of observations on your system. And one reference I like for describing this result is here from Elias Feinberg in 2022. So starting in the 1970s with the work of Rubin, Pearl, and others, there began a program, a research program that started to introduce some assumptions about the structure of the system to nevertheless deduce unique values for your causal effects given observations of your system. So I like to think about these kind of problems with this type of signature. So there's typically some quantity you want to estimate, your query. There's some measurements you make on the system, your data distribution, and then there's some assumptions you might find plausible for your particular application at hand. You can think of causal diagrams, assumptions about the functions relating different variables, such as independent noise terms, independencies between counterfactuals, and so on. These are all assumptions that will might help you uniquely compute the value of your causal effects. And so what's really happening when you introduce assumptions and make observations of your system is that you're constraining the set of possible models that would be valid explanations for your system. Right? So these different assumptions will constrain the models, create different subsets in this initial set of potential models for your system. And when you say that you're computing a causal effect or that you're inferring a bound and so forth, what you're doing is characterizing the set of causal effects that are implied by all the models in your subset. Right? So for instance, in red here, you know, if you have a little diagram and you observe many different things, you might be able to uniquely identify the causal effect, which means that all models in this red set all map to the same value of the causal effects. Now, in most cases, this won't be the case, and you're left with some sets of possible causal effects. And the problem of bounding, more generally, is about characterizing that set of causal effects. And so one very interesting property in my view is that already in the 1990s, Mansky showed that only observing your data distribution, the set of models that are constrained by those observations already shrinks the set of possible causal effects that would be possible values in your setting. Right? And not only that, he was able to completely characterize this set, that is, give a bound that is tight. So in other words, you can always find two different models in this blue set that will evaluate exactly to the lower and the upper bounds that he gave in the 1990s. And this is remarkable because a priori, we have no reason to expect any logical connection between interventions and observations. I mean, there are some implicit causal assumptions in this setting, but very, very basic ones. And yeah, so I mean, there's no ontological leap here. And this is okay. You can get a lot of inference just from this result. So you see that the width of this interval is given by 1 minus p of x. And if that value is small, then this already gives you a lot of information on the causal effects, and you can act on it and work with your application without making a lot of assumptions. To some extent, I find it maybe a little bit unsatisfying, especially for some settings. For instance, if you were to find that two variables are independent, right, x and y being independent, you would expect that intervening on one doesn't have an effect on the second one, right? So you'd expect that your causal effect of x and y is identified and uniquely given by p of y, instead of merely bounded, like Mansky said. So this is not an immediate property, an immediate consequence of your starting assumptions, but it's a reasonable expectation you may have. And this property in the literature is called faithfulness. It tells you basically that every independence you observe in your data has an underlying structural explanation. That is, independencies in the data are a reflection of separations in the underlying causal diagram. And this is very often used in the causal discovery literature, where, and all of this can also be encoded in a graphical abstraction called a partial ancestral graph that I will be operating on, so it will be relevant for later. And with faithfulness, the key of faithfulness here is that it will allow us to further constrain a little bit the class of models that will be compatible explanations for your system. And then the key would be that maybe this smaller subset of your models will then map to also a smaller set of interventional probabilities. Right? So maybe faithfulness entails a lot more information, and you can get much tighter bounds or tighter bounds with this assumption. The question that I'm trying to answer in this paper is exactly this one. To what extent faithfulness implies tighter bounds? And so Okay, before going here, this sounds a little bit overwhelming. So the key of faithfulness really is that it induces some structure. So the independencies give you some structure in the underlying models. And that structure will imply a decomposition of your causal effects, right? And that decomposition will be the key to provide you tighter bounds. So the units of this decomposition were introduced by Tian and Pearl, I think in 2002, sorry, not 91, if I'm correct, in a UAI paper as well. And so he introduced these so-called C factors, right, here denoted with a Q, that are themselves interventional probability distributions, and you can think of them as the building blocks in most traditional causal inference programs. So it's not too important about what these C factors actually mean, but what I'm trying to illustrate with this picture here is that there's a small set of operations on these C factors that allow you to further decompose a probability or interventional distributions into smaller C factors, themselves decompose into smaller C factors. And that's how you work into identifying causal effects with this iterative procedure. So this can be represented in this tree. So each one of the edges, right, represents some operation on these C factors. And what I'm basically saying, for instance, is that QZ can be obtained from QXYZ, which is the observational distribution, by some function, and similar for QXY from QXYZ, QX from QXY, and QY from QXY. Thanks. And I'm showing also in gray what these C factors, how these C factors are actually defined. But as I said, that's not too important. Now, you can do the same thing with your query, right? Your query can be expressed in C factors, and these C factors can be iteratively decomposed with these operations. And what I really like about this presentation, and Juan Correa showed this recently, is that you can think of identification as matching these leaf C factors across the two trees. So you have one tree for your data, you have one tree for your query, and identification can be thought as a process of matching these required C factors for your query to the ones you have from your data. And if you're successful in matching those, you can then work back through the tree and get a unique value for your causal effects. Okay. So I like to think about this as a hierarchical perspective on identification. Is that to identify the task of identifying a causal effect can be decomposed into subtasks, and these subtasks into further subtasks, and so you can solve each of those, and then all the results you get a final value for your. Now, the implication of this strategy being complete is that whenever you cannot match a required C factor from a query to one from your data, you would say that your causal effect is not identified. And this is the case, for instance, if you just slightly modify the causal diagram on the right with adding this directed edge between S and M. And I should say also that you get this decomposition as a consequence of the structure of the causal diagram. So all these decompositions are all a consequence of having knowledge of the causal diagram. And the key observation that I'm going to make for this work is that even though you cannot match all components, you can always bound a C factor by a larger one. So in this case, you can, there's always going to be a function that bounds QY as a function of QXY, which is available in this setup. And with this proposition, with this theorem, you can work exactly as in traditional identification algorithms, just replacing QY with its upper and lower bounds, and then work back to the tree and get a lower and upper bound for your initial query. So why am I saying all of this? I told you that I wanted to be a little bit more data-driven, and here I'm conveying all of this information based on a causal diagram. So this is kind of a maybe simpler introduction to what I'm going to describe next. And the idea is simply that exactly the same principle holds if instead of operating on a causal diagram, you operate on an equivalence class of causal diagrams, which is the graphical abstraction that would be implied by your data. The edges will be a little bit different. There's typically going to be less of a decomposition that you can do, but it's the same overall structure of matching and bounding rules. Okay. So I'm not going to go on that part. So first, let me show you what an equivalence class for diagrams implied by independencies look like. So we've had some examples in the previous talk, but essentially this is the picture that you can have in your mind. So we start from a number of independencies that we may have tested in our observational data, and they'll be established as facts of your distribution. So there's again a typo here. It should be W independent of Z in the first independence and not S independent of Z. And essentially now the edges in this graphical abstraction have a slightly different interpretation. You see there's some additional edge marks and some V's somewhere. And all of this is meant to illustrate what are the invariant properties of all possible causal diagrams that would be compatible with the data and which ones can be changed. So for instance, in the bottom, you have 3 members of the equivalence class that are kind of summarized in this flag. So for instance, you see that the WX edge could be just an unobserved confounder between WX. There could be a directed arrow between W and X, or there could be both. Right, so these are the kind of undeterminacies that are kind of encoded in the path. So as another example, whenever you have a V on top of a directed edge, that means that there's no unobserved confounder between Y and S in this case, in any of the graphs that are implied by that are kind of encoded in this equivalence class. So there is quite a lot of information that is given in the pack, and that will be key to improving upon the more worst case bounds that are given by Massimo. Right. So let me wrap up. So here is an example of bounding a query given data and this equivalence class. So exactly the same structure applies, right? You write your query or your observational data in these with the C factors, you decompose them, and there's different operations you can apply to further decompose each one of those. And the key contribution we make in this paper is to show that the C factors can always be bounded from larger ones. And then you can work back the tree to get a bound for your query. So here in blue is an example of the kind of expression that our algorithm returns, right? To some combination of conditional distributions. And here you have the expression for the upper bounds. So if you know a little bit about Mansky bounds, you recognize that these are different, and you can show that these are types. So I want to conclude with this slide, which is a picture a little bit of what you can think of end-to-end causal inference, which is this research program that starts from an equivalence class of your data and then tries to infer as much as possible about a query and given a data distribution. So here there's many variations that you can imagine. As I talked about causal effects, we could think of counterfactuals, transportability queries, we could think of data in different domains and so forth. So there's a large spectrum now of open questions that you can start to to tackle with these concepts. Thank you.
Thank you, Alexis. Questions for Alexis? Murat, yeah.
Hello. Thank you for the great talk. Just a quick question. So I guess the idea is for each C component that's not identifiable, you get a bigger C component that is identifiable and use that to bound, right? That's what you said. Can you comment on the tightness of this? Because one would think in the ID expression, if you put all these bounds, you get a bound, but the tightness is not clear to me. You use claims tightness ID, right?
So I claim tighter than the worst case bound by Mansky, but in fact, one big limitation, which is why I titled the paper with 2 words bounding, is that these bounds are not tight.
Okay, I misunderstood them. Okay, thank you. Thank you.
Are there other questions? Yes.
You said the Mansky bounds were for discrete variables, right? And all your work is also on discrete variables. So you considered the continuous case of proof.
Yeah, so another limitation, all this applies to discretely valued systems. The proof strategy, I mean, it's not even clear to me that you can do this in the continuous.
More questions?
Just a comment, you probably can with continuous outcomes. But
Correct, continuous outcomes is fine.
You can derive the bound, Mansky's bounds for continuous X, but they become non-informative.
Okay.
So, except if you are willing to make smoothness assumptions on how the outcome depends on the treatment.
So you need bounded random variables, I guess. Or something.
Questions? Yes.
Ended up figuring into the end results. So basically, if I understand correctly, the role it would have played was in the notion of a Markov equivalence class for the partialized ancestral graphs, right?
Correct.
So, yeah, okay.
Yeah, so very quickly here, the key to improving is that in this decomposition, while one of these C factors is not identifiable, the other one is. So that's information you can exploit to get tighter bounds. And this is something that's implied by the structure of your graph, and therefore it works. Thanks.
Okay, thank you, Alexis. So our next speaker is Armin Kekić. Armin will tell us about targeted causal reduction, a method that simplifies complex scientific models into concise, interpretable, high-level causal factors using interventional data. Lots and lots of interventional data.
Can you hear me in the back? Does that work? Test. Okay, good. Okay, today I'll talk about targeted reduction of causal models, which is a way of learning high-level causes of phenomena that are occurring in simulations. This is joint work with Bernhard Schölkopf and Michel. So simulations are important for scientific discovery and decision-making. There are many examples, some of which are here: biology, climate science, epidemiology. Maybe the most notable example is recently epidemiology, where we had very harsh government interventions as a consequence of results of simulations. And as you see here, most of them have some sort of phenomenon that you're mostly interested in. In this case, it's does this fruit fly fly? Here it's something like the global average temperature over the next 100 years. And here it's something like the number of severe cases over some time frame. And even though simulations are important, they can be high dimensional and difficult to understand. However, explaining simulation results is important if you want to make good scientific discovery and informed decision making. So the goal of this work is to develop a method that finds high-level explanations for why certain phenomena happen in simulations. And I probably don't have to convince this audience that causal methods provide us with a principled way to reason about cause-effect relationships. But before I go into how we use causal methods to explain phenomena in simulations, I'll give a quick example from physics, or how physicists treat complex systems. Physicists are very good at extracting the most essential modeling elements and reducing it while still keeping predictive power as much as possible. Consider the system of masses that are connected by springs, and we have some random external forces acting on the masses. Now, if we care about how the system moves as a whole, we don't need to model all of the degrees of freedom of the system. We can find a reduced effective description which still is good enough and captures what we need to know about the system with respect to what we want to explain. So in this case, if we say care about the center of mass velocity along this diagonal axis, we can summarize the system variables as the center of mass velocity. And similarly, we can summarize the external forces as something like the net force along this diagonal axis. And while we lose some information here, we still keep the relevant parts which are important in order to describe the phenomenon that we care about. And what's more is this high-level description actually tells us something about the system, the underlying system that we want to study. So in this case, for example, balls with higher mass are important for the center of mass velocity. And something like the external forces that are opposite cancel out along this diagonal axis, so only the net force matters in this case. And the method that we're presenting here, targeted causal reduction, tries to generalize this approach for understanding scientific simulations. So the one-sentence summary of what we're trying to do is we treat the simulation as a low-level causal model, and we try to learn a map to some smaller high-level causal representation. So this is the diagrammatic overview. We have a simulation. We treat this as a structural causal model L for low level, and we define some high-level causal model, which you can see as some sort of approximation of what's happening in the simulation. And we learn a map between those. So we learn a map tau between variables here and there. And the target is the phenomenon of interest that we care about, and we assume that this is given. So we assume that this can be measured in the simulation. And what we use to figure out how this map should work, we intervene in the simulation through low-level interventions, which you can see as somehow probing the system, and then we can observe what the effects are on the target. And these low-level interventions, we also map to the high level through some map omega. So we have three things that we need to learn. We need to learn the map tau between variables. We need to learn omega, the map between interventions, and we need to learn the parameters of this high-level model. And this we will do through something which we call causal consistency loss. So here are the elements. We have two SEMs. We need to map between them. And first, I'll go into some background of what SEMs are and what it means for a map from one SEM to the other to be causally consistent. So very quick summary, structural causal model, SEM, is a triplet that consists of a distribution over exogenous noise variables, a directed graph, which tells us something about the causal relations between variables. And we have a set of structural equations which set the endogenous or observed variables as a function of the direct parents and exogenous noise. And this SEM entails a joint distribution over the endogenous variables. And this also allows us to reason about interventions. So interventions in this structural causal model, which we will parameterize by this vector I, change some or all of these structural equations and induce a different distribution, which we will call PI of X. Yeah? And now, since we have to relate two causal models, we want to do them in a somehow reasonable or consistent way. So suppose we have two causal models, two SEMs, one SEM L for low level with endogenous variables X and some intervention set I, a high level causal model with variables Z and intervention set J. And we have a map from low level to high level causal variables, which is surjective, so we potentially lose some information. We call this map causally consistent if the following holds. So if there exists an additional map between interventions omega, such that the following two distributions are the same. So we have on the left-hand side, we have the high-level interventional distribution. So we apply the high-level intervention here. And that's supposed to be the same as the push forward of the low-level intervention. Okay, those are big words, but the easy way to understand what's going on is on this through this commutative diagram. So we start with an observational distribution here on the left, upper left, and we want to arrive at the high-level interventional distribution. And there are two ways in which we can do this. We can first intervene in the low level and then map to the high level. Or we first map to the high level and then intervene with a high-level intervention, which is given by omega. And if those two paths are equivalent, or if they lead to the same distribution, then we call this causally consistent. In practical applications, this is a bit much to ask. So a related property is approximate causal consistency, where this approximately commutes, and these are roughly the same, and we will use this idea later on to learn our reduction. Okay, how do we apply this to simulations? We have some sort of simulation and with variables x, and we treat that as a low-level causal model, and we define a high-level causal model here on the right-hand side with a particular structure. So we assume the structure is fixed. We have some y, which is our target or the phenomenon that we care about, and we assume that there are n independent causes which cause this phenomenon. And the map to this high-level model of the phenomenon to y is fixed and known. So we assume that whoever runs the simulation can give this to us. And what we need to learn now is maps from the low-level variables to all of these high-level causes. And what we use as a learning signal is interventions. So we intervene, or you can think of probing this simulation, observe what happens to the target, and these interventions we also map to the high-level model. I'll come to how we implement these interventions in a bit. So summary, low-level SEM, high-level SEM with a fixed causal structure. We map variables and we map interventions. We assume that we use shift interventions. So shift interventions are a particular kind of soft interventions where we just take whatever comes out of the original structural equations naturally and just shift it up or down a bit. Right? So we keep the relationships with the parents. How we implement this in simulations, I'll come to this in a bit. And since you can think of our main output being these maps, so these maps omega and tau are the main output, which will then somehow try to explain what's happening in the simulation. So in order to make those interpretable by design, we constrain them to be linear. So we map linearly the interventions and states. And similarly, we assume that the high-level mechanism is also linear Gaussian. So these z's are independent and they linearly contribute to y, and the exogenous noise here is Gaussian. Okay, so how do we learn this thing? So as I said, we want to make this map or this reduction approximately causally consistent. So we define this push-forward distribution of the low-level interventional, so one branch of this cumulative diagram. And we compare this push-forward to the high-level interventional distribution. So we compare this to a KL, and we take the expectation over all interventions that we apply in our simulation. Yeah, so these two terms exactly correspond to each of these branches. So first intervening, then mapping, or first mapping and then intervening with the high level. Yeah, and we reduce this discrepancy between those two during training to find the maps and the high level parameters that we need. Okay, we also investigate this theoretically. So under some additional assumptions, we show that we can find a unique solution of this reduction up to multiplication that actually has perfect consistency. And we use this for two things. So we use this to verify that our algorithm actually converges to optimal solutions in this case. And also we use this to figure out what kinds of solutions our reduction learns. If you want to learn more about this, come see us at a poster this afternoon. Okay, maybe just to make this very explicit, so what are the assumptions? You might think, okay, in SEM, my simulation doesn't look like an SEM, but here are the assumptions that we need for a simulation to work for us. So we assume that there exists a target that we can measure in the simulation. We assume that there exists a notion of shift intervention, and we assume that we can sample from the simulation under interventions. And in particular, we do not have to know about the causal structure of the low-level simulations. Our method doesn't use this, so we only have samples, interventions, and their effects on the target. Okay, and here is an example of how we do this. So in order to, since our output is somehow an explanation, we use some sort of high school physics simulations to see if what we get out makes sense. So we simulate a ball in a double well potential. So the ball starts on the left, makes it up, and then either goes to the right or to the left. So there is friction. So usually the ball makes it to the hump, and depending on the initial conditions, it either makes it on the other side or it doesn't. So here is one of those trajectories here that you see. So it makes it to the middle hump and then goes over. And the way you simulate this is through some numerical scheme on some discretized time grid, using some forward Euler, for example. And this is just an integration of the Newton's equations. And the way we implement interventions here is we sample some sort of random noise that corresponds to shifts in velocity, and we apply them here. So you can think of this as random forces jiggling on the ball that we run through the simulation. And in this case, for this particular set of initial conditions, actually this changes the outcome at the end. So the target that we're trying to measure here is the final position of the ball, left or right, well, basically, very simple. So the variables are velocities and positions over all time steps. The interventions are these shifts, so we only shift velocities. We could also shift positions, but we don't, so we have zeros here. And the target is the final position at the end of the simulation. So here's the low-level causal model. We know what the causal model is because we control everything, but our method doesn't have to know about this. And we learn the simplest possible reduction. We have one cause, one effect, and one intervention. And these are the maps that we have to learn. So tau 0 is fixed and known. We just copy this value. We learn a linear map to Z1 and learn a linear map omega 1 to the intervention J1. Okay, so what do we get out of this? So here on the top, you see the probability distribution of trajectories that we have. So we go either to, like, we go to the middle hump and then make it up or down. And the learned tau and omega weights that we have for this simple reduction are here. So we have tau here, and what we see is that actually this reduction pinpoints the crucial point in the simulation where the decision happens whether or not the ball goes to the left or to the right. But the weights for the velocity are given here. So that basically means if you have positive velocity at this crucial point where the ball is in the middle hump, then we predict the ball to be more likely to make it to the other side. If it's negative, then not. Similarly for omegas, which encode interventions, basically tells us if we at the beginning give the ball an extra kick, it's more likely to make it to the other side. So this is sort of the types of maps that we can look at regarding the simulation routine. Just a quick example of another experiment that we ran. This is the system of springs and masses that I showed you at the beginning. So we have 4 springs, 4 masses and 4 springs. And the target of this is, so we simulate this motion, and the target of this is the center of mass velocity along this diagonal direction at the end of the simulation. And as interventions, we again apply random shifts to the velocity, which is kind of jiggling forces at the balls. And in this case, we learn two high-level causes in the reduction. So the weights, the tau and omega maps for the first cause are shown here, and the tau and omega weights for the second cause are shown here. And what we see is that so the dashed lines correspond to the x direction and the straight lines to the y direction. So the causes actually focus on 2 independent reasons for why this thing might move in the diagonal direction. So one in the x and the y directions. And additionally, we find that since they have different masses, so 1 is the lightest and 4 is the heaviest, the weights that we give, the relative weights that we give to each of these masses is also proportional to the weight that it has, so to the mass that it has, which is also consistent with what we would expect from the physics of the simulation. So let me quickly summarize this. So we treat the simulation as a low-level causal model. We assume that there exists some sort of target or phenomenon that we care about. And we learn a map to a high-level causal model with a fixed causal structure in order to explain the causes of the phenomenon that we care about. And we use low-level interventions and their effects on the target as a learning signal. If you want to know more about this, come chat to us at our poster. Thank you very much.
If you have many questions.
I have a couple of questions. One is that basically you don't regularize this, right? So you assume every time you have an idea what what is the model reduction you need to do? Like you want to find two causes or one cause? In reality, you must have some sort of like model selection, right? So you.
So yeah, I glossed over this. So in the when we have, so we do assume, so we I'm sorry. Okay, so in our reduction, the number of high-level variables are fixed. But what can happen is some sort of mode collapse. So if you have multiple high-level variables, what can happen is that the high-level model actually ignores many of the causes and just only puts all of the information into one. And we do regularize this. So I glossed over this a bit. So we actually also make this what's called constructive transformation. So we penalize too much overlap on the low-level variables between maps. So in some sense, we force them to focus on different things in the inputs.
Thank you for your great interesting talk. Could you elaborate why the high-level structure causal model is identifiable? Is linear Gaussian assumption is crucial for your identifiability results?
So what we say is that there is the solution that leads to perfect consistency. The solution that leads to perfect consistency is identifiable up to multiplicative constants, and we do assume that it's linear Gaussian. So for other models, it's not necessarily clear how to do this, but actually it gives us a good idea of what the kinds of solution that we find. Maybe this goes into too much detail, but actually these solutions in the linear Gaussian case, if we can actually have a good idea of, for example, if you have a linear chain as your low level, which is actually somehow, in some sense, what happens here. This sort of resembles a chain graph, actually, with 2 dimensions. Then the solutions that we find in our theoretical results are somehow similar to what we find here. So they do give us some insights also for cases which are nonlinear. So this is not a linear model, but it still somehow gives us a good idea of what comes out of it.
Okay, thank you.
Thank you for the talk. Just to like a clarifying question on the workflow of the TCR algorithm. Do you assume the structural knowledge of the high-level model, or is that learned at some point in the procedure?
Yeah. So what's fixed is the causal structure. So we assume that these causes are independent, and that the number of causes are also fixed. What we learn is the mechanism that relates them. So we assume they're independent, but we learn these alphas that weight these different causes.
A quick one. Can I?
Yeah. Thanks. So just a quick question. Your definition of your loss function. Sorry, consistency. Use the KL divergence to measure the discrepancy between distribution. Is there a motivation for this choice of divergence? Is it computational, theoretical? Could you consider either divergences or distances?
I guess we could also consider others. I mean, given that we assume that this is Gaussian at the end, this makes it simple and computationally tractable. In principle, there are other ways to do this, but we haven't.
Okay, thank you.
Yeah. Can you put any interpretability constraint on Z? Because when you reduce a model from the physics perspective, you are trying to reduce to some interpretable variable that you can intuitively understand. But here, you let the system learn the structure of each high-level variable, right?
Yeah, so the constraints that we put are exactly that we have linear maps, independent causes, and a linear Gaussian high-level model. This makes understanding this a lot easier. I mean, in principle, we could make those more complex, but then you'd have to have like a second layer of interpretation on top. So the interpretability constraints are actually those. So linearity and independent causes. Actually, I mean, we don't, it's true that we don't exactly get the center of mass. but we kind of do. I mean, so the weighting that we find, for example, here is that it corresponds to the weights or the masses of the balls. Of course, we don't get the physics equation out. That's true.
Thank you.
Hello. So first of all, thanks for the great presentation. Maybe I missed this point, but I was wondering what the rationale for assuming that Y is an effect of these causal abstractions is.
I mean, in some sense, this is the main goal of this is to figure out causes for Y, right? I mean, we have some effect, say the position of the ball at the end of the simulation, and we want to figure out what has led to this having a certain value.
But could Y not be a cause of some of these variables, or what's the maybe?
Oh, so sure. I mean, the thing. I mean, in principle, Y can be a cause of some of the variables that are here, and then it is ignored in the reduction at the end. So
yeah, okay.
Yeah, so this is an approximation. I mean, in principle, the structure could be different, but for example, in our identifiable results, we find this. So if you have some downstream effects, they're just ignored because the effects, like intervening on them, doesn't change the outcome.
That makes sense. Yeah. Okay. Thanks.
Thank you, Armin. Our next talk is via Zoom, so we need a minute to sit down.
Hi, everyone. I hope you can see and hear me well. Thanks to UAI and the organizers. Sorry I couldn't be there in Barcelona today. I'm presenting a work called called Characterizing Interventions in Causal Games. So I will share that now. Okay. So I hope this is all visible. Yep. So this work, Characterizing Interventions in Causal Games, is a work that is concerned with the intersection of causality with game theory. There are a number of concepts in game theory which have direct sort of analogies or theoretical bridges to concepts in causality that can be useful for us to explore. This paper specifically looks at bridging a gap that was present where it was not possible to discuss or analyze a series of interventions that are interleaving with agents making decisions in game theoretic scenarios. So we'll go into detail on that, but I'll start with a bit of background. So this work it was by myself and my two supervisors, James Fox and Michael Wooldridge, all associated with the University of Oxford. James is also with the London Initiative for Safe AI, and Michael is with the Alan Turing Institute as well. So just thanks and acknowledgements to those institutions. So we explore game theory because there's a number of concepts. I mean, the fundamental idea of strategic reasoning is to look at agents, the decisions they make, why they make them, and how to align the incentives of those agents through designing games which ensure that agents behave, for example, towards social welfare or towards a utilitarian objective or towards making a particularly malicious agent mitigate the effects of a malicious agent. And causality is really good for this because it allows us to look at the impact of interventions and allows us to model concepts which are very native in causality, like manipulation, deception, harm, blame, and map those over to game theory. And so let's start with a bit of background. I won't have to cover much here. I'm assuming with this workshop, a lot of people are familiar with the concept of a causal Bayesian network. And so, yeah, you have a variable, and we can determine that it's causally influences another variable if an intervention on the variable would lead to a change in the variable downstream of it. These graphs, each node represents a conditional probability distribution in a traditional causal Bayesian network. So the next step on from this is to introduce a concept of agency. So not just variables, but decisions being made. And so in the previous example, we kind of had that the sprinkler depends on rain and the grass depends on whether the sprinkler is on and the rain is on. With causal influence diagrams, we extend the notion of causal Bayesian networks to accommodate different types of nodes and different kinds of variables. So we have, we show that something is a decision node by a square, and that decision node means essentially an agent can choose the conditional probability distribution across its actions based on the parent variables that are going into it, the parent CPDs that are going into it. And then we have diamonds, which represent the utility variables. And these represent kind of the reward function of the agent. And so we have variables which are chance variables, those of nature, decision variables, those that are made by agents, and utility variables, which are those that are sort of representing the rewards of these agents. On my side, by the way, I'm like my camera's slowing down a little bit. I just want to check that everyone can still hear and see me okay. Yes. I'm going to continue assuming so. Yeah, okay. So the next step on from this is a concept that was introduced in 2021 to 2023, which are these concepts of mechanized graphs. So a mechanized graph contains within it these mechanism variables where you can map the specific policy that is used to decide on the CPD and visualize the dependencies between these policies. So for example, in this scenario, the policy of the sprinkler is dependent, it causally influences the graph, the grass. And so there's an arrow between the mechanism variable of the grass and the sprinkler. And we'll go into a little bit more detail on a more in-depth example where I'll be able to show you why it's important to be able to map mechanism level dependencies. But very broadly, the important thing to understand here is that these things are very implicit. And in causal graphs, we have this concept of deseparation, which allows us to map like what variables causally affect other variables. Mechanized graphs make relations like that very explicit by showing arrows between mechanism variables. And I'll go into that in just a second. But first, let's start with the example that I'll be using throughout this presentation. So we have in this example a mechanized made, or you can call it a causal game. So you have a variable which says whether a student is lazy or hardworking, and that will affect the decision of them to go to university. Those things will together also inform whether what the student's utility or reward is, whether they're happy. It also then affects whether they're hired by a company they want to go towards, and then so on, like the recruiter of that company is happy depending on whether the student is lazy or hardworking and whether they were hired. So you can map these kind of causal dependencies in this kind of graph, and you can map this two-player game as this causal graph. I've just changed the letters here, and we then represent the policy functions. So these are these mechanized nodes which feed into the nodes of the graph, which map what the policies of those associated with deciding those probability distributions is. So for example, the student might have a number of possible rational decisions that it could make, and the node representing pi d1 shows what their policy is for deciding over those decisions. So it's their decision rule, basically. And the reason we have this is because then we can map together the links between the specific policies. So because, for example, here, the policy of the student affects the decision of the student. So pi d1 affects d1, which links to the utility of the recruiter, U2. There we draw an arrow between pi d1 and pi d2. And in the paper, we go into depth into what are called reachability conditions. These are derived from the concept of deseparation. And essentially, we can encode what the concept of rationality is for the agent in a series of graphical conditions, but also conditions to do with probability distributions. So in the paper, we go into detail, in the 2023 paper, reasoning about causality in games, it goes into detail about what the graphical conditions are that correspond to different notions of rationality. One very obvious notion of rationality that is used in game theory is best response. So every player is completely self-interested. And if every player is completely self-interested, they will play their best response to the scenario set out in front of them. And in the 2023 paper, that is mapped to a graphical condition on the causal graph, which corresponds to either, it corresponds to the policy of the decision maker being deseparated from the utility of of another player, given that the decision node and its parents are visible. So that's all explored in the 2023 paper. This paper expands on that and comes up with sound and complete set of primitive interventions that allow us to do the kind of interleaving that I was talking about at the beginning. So I'm just going to go into what those primitive interventions are, how we showed they were sound and complete, and then give you a lot of examples of the new things we can do now that we have primitive interventions. So this is going to seem pretty simple, but let's take the game we were looking at the beginning. So the first thing you can do is fix an object level variable. So as is typical in causal graphs, that means severing the incoming arrows into that node. So in this example, we fix whether the student decides to go to university or not. That's one kind of intervention. Then you have fixing a mechanism variable. So that corresponds to the same thing. You can fix the policy of the student. So maybe you fix it to 50% of the time they will decide to go to university and 50% of the time they won't decide to go to university, something like that. That's one kind. You can add a new object level variable, or you can remove an object level variable. Now, all of these composed together it covers the total set of possible interventions on all causal games. And each of these interventions is itself a causal intervention. And that's kind of the first theorem of this paper. So I've only included the sketch here, but it goes into the full explanation for how completeness is shown. And the idea here is that any sort of intervention can be done by composing different kinds of primitive interventions. So for example, you might think, okay, removing an edge is a type of intervention that you can do in a causal game. Why is that not a primitive intervention? Well, that is a special case of object level fixing. So here, to remove the edge between D1 and U1, that is a special case of fixing the probability distribution of U1 to a new probability distribution called V1, which doesn't consider D1 as a condition, as a parent node. So in the same way, any sort of intervention that you can consider can be done by composing these primitive interventions together. Now, the really novel part of this paper is allowing interleaving interventions. So until now, these were the kind of scenarios that we could model. So we can model either post-policy or pre-policy interventions. A post-policy intervention means you take a causal game. So that's, as I was discussing, these graphs which can do strategic reasoning and causal reasoning. And you say, let's figure out how each agent will behave. Then we will do some kind of intervention on the game, and we'll calculate probability distributions, which will allow us to say whether we've been able to match a specification, or whether the agents will behave in a certain way, or what the probability is of a certain outcome. A pre-policy intervention is the other way around. So I'll just go back and show you again. The step 1 and 2 are flipped here. You can intervene on the game and then calculate the rational outcomes for all free agents. The reason I put free here is that your intervention might accidentally remove agency from certain agents. So if you intervene on an agent that had a single decision and you fix that decision, that is not agentic anymore, because that node is now, in essence, a chance variable. You've fixed the probability distribution, and so you've removed one agent from the system. So that could be a case that happens, which is why I specify that we calculate rational outcome for all free agents and then calculate the probability distribution. But this kind of format wasn't analyzable before this paper. So what I'm looking at is when you can calculate the rational outcomes of, so for example, agent 1 might be able to see a certain scenario, then we can intervene on the game, and then agent 2 makes a decision, then we do another intervention, then agent 3 makes a decision. And different agents might make decisions at different times. In a lot of real world examples, this is the case, and we need to do analysis where agents have a different perspective of the scenario in front of them. It's not necessarily, the assumption that's been made until now that every agent has the same visibility on the game is just not necessarily true in real world examples. And so we allow this kind of modeling to be done, and I go into an algorithm for how to do that in the paper to calculate the result of an interventional query. There are a number of definitions that I'm not going to go into this presentation on rationality relations, which build on some prior work. But in essence, what we are doing in this algorithm is taking the game to a state which is the state that should be visible for agent 1. Then we take it back to a state that should be visible for agent 2, and so on and so forth. And we can basically do interventions until we can get the game into a state such that every agent can see the state that they should be seeing in order for them to make the decision that they want to make. So I'll go into certain specifications that we can now calculate using this framework. So let's pick a really simple example of a game, the classical prisoner's dilemma. So this is, I'm sure everyone is familiar with the idea that in a game where two agents could get a better outcome by cooperating, they actually both choose to defect because of their individual incentives, which leads to them getting a worse overall outcome. Suppose you're a game designer here, or you're some kind of malicious prison guard where your objective is to increase the total jail time for Alice and Bob, where the current total under the rationality of both players is 4 years. Well, one intervention we could do is deceiving Alice into believing she goes free if Alice and Bob both cooperate. So this is an intervention that we might want to implement in the game. Now, how can we do that? Well, this framework allows us to do that. On the causal graph, we can basically calculate what the rational outcomes are for Alice and Bob. In this case, it would be defect, defect. Then we can change the payoff of cooperate, cooperate to 0 - 1, fix Bob's policy through another intervention. And what that means is Bob is no longer able to witness further changes we make to the game. We then calculate the rational outcomes of Alice again. She changes her decision. She changes her decision. Then we can change the payoff back, fix Alice's policy so she can't see any future changes, and then calculate the probability distribution. And what this means is, I mean, if you look at this kind of game, if Alice believes that cooperate will give her a utility of 0, which is the same as defect cooperate, then her rational policy to do it would be something like a 50% chance of doing cooperate, 50% chance of doing defect cooperate, and that leads to an overall jail time of 4.5 years instead of 4 years. So the objective of the malicious prison guard has been achieved. The prison guard has been able to increase the total expected jail time for both agents to 4.5 years rather than 4 years by doing this kind of intervention. And the framework makes it possible to analyze what the effects are of such interventions. So that was a quantitative example. You also have qualitative examples. So in a qualitative example, you're considering the structure of the DAG, not a DAG, actually, it has cycles. So of the causal graph, and you're trying to figure out how different interventions will affect this structure. So in red here, you can see the reachability path between the policy of agent 1 and the utility of agent 2. And this is what enables this blue arrow to be drawn between pi d1 and pi d2. So in essence, because the policy of d1 affects the utility of player 2, then the strategy of player 2 is affected by the strategy of player 1. And if you break one of these reachability paths, so if you, for example, fix d1, that will inherently remove the arrows, the red arrows, two of the red arrows shown, which will break the reachability path and cause a side effect of the blue arrow also being removed. And in the paper, we go into exactly how you can calculate what the mechanism level side effects are of doing object level interventions, but it allows us to look at really interesting new properties of games. So here are two properties that we look at. The first is the robustness of an incentive. And so you want to know something like, hey, like if I intervene, or if I want to break a kind of incentive in the game, how many objects do I need to intervene on to break that dependency? And we can measure that by looking at reachability paths. So the number of reachability paths that need to be broken in order to break a mechanism level dependency is a measure of how robust an incentive is between two players. The second thing we look at is how disruptive is an intervention. So if the structure is maintained after an intervention, that means the intervention wasn't that disruptive, and we call that incentive invariance in the paper. And so these are two measures that you can now do. We also, I'm worried I'm a little bit going over time, so I'm going to just wrap up here. We also go into the concept of commitment. So commitment is this idea that one player can gain an advantage by revealing their revealing information to another player. So in this example here, player one can actually gain an advantage by picking the policy B, bottom, and that actually leads them to get a higher expected value than if they had hidden what they were going to do. And that is a well-known concept in game theory, but actually quite difficult to model with multiple agents. With this framework, we can model such concepts quite simply. And so, yeah, this has been characterizing interventions in causal games. I'd be happy to chat more. I mean, yeah, of course, open to questions, but also emails and Twitter and so on. Thank you so much.
Thank you, Manuj. Questions for Manuj?
Thank you for a very interesting presentation. I was wondering a bit about the cyclic dependencies in the graphs that you showed between the policy nodes. Should I think about those as what are the meaning of those edges? Are they causal, or and if they are causal, then what kind of mechanism do they represent? Some kind of equilibrium model, or?
Yes, so this is a really good question. The cyclical dependencies do represent that the policies of the agents are mutually dependent because in this case, there is a reachability path from the policy of D1 to the utility of player 2, but also from player 2's policy up till the utility of player 1. And yes, well, I guess what it means is, yeah, it can so I think the results show that there is at least one equilibrium, and that mutual dependency shows that, but it doesn't really tell us much more about, you know, the nature of those equilibria and so on. What we can say also is that the meaning of this arrow depends on your definition of rationality. So if we go with, for example, best response rationality, a cyclical dependency between policies will correspond to there being a Nash equilibrium. But there are other kinds of equilibria, like stable hand equilibria and so on, which correspond to different rationality relations. And the structure of the arrows relating the policies will look different if we're talking about different kinds of equilibria. So it is a little bit dependent on what our definition of rationality is. And typically we would like to have like a shared definition of rationality among all agents. So, you know, it would be very difficult to analyze if one agent had, you know, was going off best response and another agent was going off something more silly, like trying to maximize the utility of all agents or something. That would, yeah.
There are more questions, so we should probably let others ask questions.
Sorry, yes.
No worries. Questions? Can you tell us a little bit about how these results can be applied to AI safety settings?
Sure, yes. So I think there are kind of two ways that these results are important. Often we're going into a world where AI is becoming more agentic and is able to act on, and by agentic I mean simply it's able to act on long-term objectives and is doing multi-step actions to achieve those objectives. And to have visibility on how we can incentivize AI systems to behave in alignment with human incentives, you know, you need complex ways of analyzing how incentives behave under intervention. The second thing I would say is important is that AI systems are increasingly taking on human workload, and there is something to be said about the retaining human agency in the world. And these models also help us understand how much agency a player has in the system. And it will be good to retain a baseline level of agency with humans.
Thank you, Manuj. Oh, there's one more question for you.
Hi, thank you for the great talk. I'm just wondering about the last step of all your algorithms where you calculate the probability distribution over the endogenous variables. So where does the randomness come from the exogenous variables? And if so, do you assume that they're known?
I didn't catch the very last words. Do I assume that they're what, sorry?
They're known.
They're known. Oh, okay. Yes, I would say so. The second last step of all of the algorithms is calculate the policy of all free agents. And so you need to know what every agent's policy is to be able to do a calculation of probability distribution. And that comes from basically what is their rationality definition. So the randomness comes from the fact that, well, firstly, the nodes are all conditional probability distributions. The arrows represent the fact that, like, parents. So if a parent changes, all of its downstream children will also change. That's kind of where the probability distribution comes in. And okay, so I guess there's also some randomness in that you can have multiple rational policies. So in any of the games I described, there might be 2 or 3 things that a player could do that are equally rational. And then it's typically, like the way I've modeled it at least, is that it chooses uniformly randomly across its rational policies. So that's a source of randomness as well.
Thank you very much for the wonderful talk, Manuj.
Thank you so much.
Next speaker is Nicholas Bishop, and we'll be talking about multi-armed bandits. Yeah.
So I'm Nick Bishop. So as Bruce said, I'm going to start talking about causally abstracted bandits. This work is a joint work between lots of different talented people, ranging from people at Oxford, University of Bergen, and the University of Warwick. And I'd just give a special shout out to Fabio Zennaro, who's not here, but he really drove a lot of his work forward. So we've already seen today a talk that talked about causally abstracting between 2 causal models and trying to relate 2 causal models together. And so causal abstraction is becoming this increasingly kind of powerful paradigm to relate causal models. But there's a kind of a lot of questions still to be answered. So one of these is, if I have an abstraction between two causal models, can I kind of transfer decision-making policies between them? Like, how might I even go about doing that? What are the issues? What might the pitfalls be? So to kind of answer this question, we kind of introduced a new kind of multi-armed bandit problem called causally abstracted multi-armed bandits. Okay, but tries to kind of model this approach, and we kind of explore generic problems in this framework to try and get an understanding of how an abstraction might be used to kind of transfer decision-making policies across causal models. So before I can introduce this new bandit model, I need to introduce causal abstraction. So we've already seen one kind of causal abstraction framework today. This one is slightly different. So I'm going to assume that I'm given 2 SEMs, denoted by calligraphic M and calligraphic M prime. And I'm going to define an abstraction between them using a framework called alpha abstraction, which was introduced in a paper at UAI. And an alpha abstraction is just a tuple of 3 things, V, small m, and alpha. And I'll abuse notation slightly and refer to this tuple as alpha generically, and use alpha to denote when I'm applying it to certain causal models. So what does this tuple actually look like? Well, this V term in the tuple is just a subset of relevant variables in your base model. So this is just a subset of variables in M that you want to abstract to some other model. Small m is just a surjective map from these relevant variables to variables in your abstract model. So this is just saying, okay, if I take a bunch of base variables, what abstract variables do they map to? And lastly, you have this collection of maps, alpha. You have one alpha map for every single abstract variable, which tells you how the variables, in your base model, how their values map to values in the for the abstract variables. So I'm just using D here to denote the domain of variables in models. So this is kind of best illustrated with an example. So let's consider kind of 2 simple causal models here, where I have a treatment with a mediating effect and a treatment with no mediating effect. And let's say in the first causal model, I have 3 different interventions. So I can pick from 3 different treatments. And then in the second model, I only have 2 treatments available to me. So one thing I might do is just define a very simple abstraction here where I map
where my relevant variables are t and y. And I'm going to map t to t prime and y to y prime. So I'm basically going to forget the mediating effect, right? And then all I need to do is define my alpha map. So in this case, I'm mapping the zero treatment in my model to the zero treatment in my abstract model. I'm mapping the one treatment to the one treatment in my abstract model. And because I only have two abstract models in my, treatments in my abstract model, I'm also mapping the two treatment to the one treatment in my abstract model. And I'm just going to use an identity mapping for y, right? So once you have this kind of alpha maps, this naturally also defines a mapping over interventions as well, right? So if I want to set t to 0 in my base model, a natural thing to do would be set t prime to 0, right, in my abstract model, because I'm mapping t equals 0 to t prime equals 0. And likewise, these two interventions for treatments 1 and 2 collapse into a single intervention in my abstract model. So once I have this intervention, the question is it any good, right? And we've already seen a kind of commutative diagram that illustrates kind of what you might want from an abstraction. Alpha abstraction has a very similar idea. So if I take some intervention X, I can do a couple of things with this. The first thing I could do is just abstract it, right? I could work out what the corresponding abstract intervention is, and then I could intervene and get an interventional distribution over some variable of interest in my model. Or I could just intervene immediately in my base model and then abstract the output variable that I get out to some abstract variable in my abstract model. Now, obviously, what I would like is this diagram to commute, right? So I would like intervening and abstracting to be the same as abstracting and intervening. And if this happens, we say that the model is interventionally consistent. I'll also use the term exact as well. So obviously, in real world scenarios, you're probably not going to have this like perfectly nice commutative diagram. You're going to have some error. Okay, and this is kind of denoted by going right and down versus down and right. And I like this error to be small. And moreover, I like it to be small across all the possible interventions I have. And so this is, termed the interventional consistency error. So if we were to write this out, it looks a little bit scary, but if we kind of just break down what we're doing, we're basically looking at the worst case difference between intervening then abstracting and abstracting then intervening, right? And we're taking a maximum over all possible interventions, and we're measuring the difference in these distributions with a Wasserstein distance. Our choice for Wasserstein distance is motivated by something we'll see a bit later, but you could use any kind of divergence measure you wanted. Okay, so that's causal abstraction in a nutshell. The other thing I need to introduce is just causal multi-arm bandits, to be very brief. So a causal multi-arm bandit is just a multi-arm bandit problem where each arm corresponds to an intervention in a structural causal model. And we have the reward is given by some variable in our model. So in this case, I have 3 interventions here that correspond to setting different treatments. And, I have 3 arms or slot machines, whatever you want to call them, that correspond to those interventions, and the reward I get is the value of y under those interventions. And that's just a random sample from the interventional distribution. Okay, so typically for causal, for bandits, we use some regret benchmark to evaluate how good our decision-making policy is. So here's a very common one called the simple regret, where, what I want is my final action to be good in expectation compared to the best intervention I could have made in my causal bandits. Likewise, I might think about the cumulative regret, right? Where, I will compare against the best fixed policy, which is here just repeatedly taking the optimal intervention over and over again, and compare that against the, expected reward of the interventions I made through some time horizon t. Okay, so with all that being said, I'm going to introduce CMAPs in a quite informal way. So let's imagine we have 2 of these multi-arm bandit problems, where one's defined on M and one's defined on M prime. And we have an abstraction between them. We refer to this kind of tuple of 2 bandits and an abstraction map as a causally abstract multi-arm bandit problem. And what we'd like to do is ask, well, can we transfer information between these CMAPs, right? And you can define lots of different kinds of transfer problems here. So you might be interested in saying, well, maybe I've ran a bunch of times and, ran an algorithm in my base model, and I'd like to transfer it to my, transfer the policy to my abstract model. Or maybe I want to go the other way. Maybe I want to learn decision-making policies for both models simultaneously and exploit alpha. There's lots of things you can do here. Just because we're just initially proposing this framework, we kind of look at a bunch of simple policies to try and get an understanding of exactly what's going on here. Like what can we use alpha for? So the obvious question is, well, maybe if I know what the optimal action is in my base model, I can just abstract that intervention and it will be the optimal intervention in my abstract model, right? So sometimes this is actually the case. So if we look at this kind of model again, where this time the treatments in both models are binary, and here the matrices are just determining, for example, the 0.2 in the top left-hand corner of the top left matrix corresponds to the probability that the mediating effect is 0, given that the treatment is 0. And the yellow matrices here correspond to abstractions of variables. So here I'm mapping, t equals 0 to t prime equals 0 and t equal 1 to t prime equal 1. And I'm doing the same with y on the other side, which I'll treat as my reward variable. Okay, and this abstraction, all it's doing is forgetting m and taking this matrix product and put it together. So it's kind of obvious in this case that you're going to get commutativity as long as you only care about interventions on T. And obviously it's actually impossible to do interventions, abstract interventions on M. And of course, this is going to preserve the optimal intervention, right? But if I was kind of a bit sneaky, what I could do is I could flip these matrices around. So I could map good interventions to bad ones and bad interventions to good ones. And as long as I flip the rewards as well, so I map bad rewards to good rewards and good rewards to bad rewards, I'll still be interventionally consistent, right? Which is great. The downside of this is actually if I operate in the abstract bandit, all the interventions will be flipped, but the rewards won't be, right? Because I only flip the rewards back when I kind of go back up the yellow path on the far side. And because I'm staying in my abstract bandit, I'm never going to do that. So actually the optimal intervention in this case becomes the worst intervention in the abstract model. So just abstracting the optimal intervention can be quite disastrous. And you might think, well, this is kind of a pathological example because you're flipping rewards. Like surely if you make the rewards order preserving, you're not going to run into these kind of issues. But you can run into other problems. So let's say now that the base model has 3 different reward values, and the abstract model only has 2, I'm forced to merge reward values in this case, right? Because I have a low resolution kind of abstract model. And even when I do this, merging rewards, you can still get an exact abstraction, but also end up with not preserving the optimal action, right? And this comes from the fact that you're distorting your rewards when you abstract. So we kind of like some sort of measure that captures the fact that when you mess around with rewards when you abstract, you can destroy the preservation of the optimal action. And so to do this, we define this kind of notion of reward discrepancy, which is kind of the worst case difference in your reward distribution before abstracting and after abstracting. Right, and now armed with this kind of reward discrepancy, we can kind of define this very simple triangle inequality that says, well, what's the difference between the mean reward, mu A, under intervention A, compared to the abstract mean reward, alpha A? And this is simply bounded by the abstraction error, which is, picking up how badly how much your diagram doesn't commute, and the reward discrepancy, which is capturing how much you mess around with your rewards, right? And obviously, if we want to preserve the optimal action, we get this very simple sufficient condition that says, well, if I look at the gaps of the expected rewards of different actions, I need this error to be smaller than half of that gap, because that makes sure the second best arm intervention doesn't become the best one and overtake the best intervention in the base model. Okay, so that's transfer of optimal actions. We can also think about like just transfer of actions in general. So let's say I have this trajectory from a bandit algorithm in the base model, and I think about this kind of offline reinforcement learning style policy where I take all the actions and I abstract them. And this is just going to be the policy that I define in my abstract bandit. And does this work? Like what's the performance guarantees of this kind of algorithm? So pictorially, you can think about it like this, and we call it the imitation algorithm. You have some player taking actions in some bandit M, and there's some imitator who observes what actions he's taking and then just applies alpha A in their mode. So, the question is how well does this imitation algorithm perform? Well, a natural benchmark to take is considering just running a normal bandit algorithm in your abstract model, seeing how that performs, and then running a bandit algorithm in your base model, and then imitating it and seeing how well you do, seeing how well you compare. Now, intuitively, you kind of expect always running in your abstract model directly to be better, but there are cases where the imitator does better, and it's given by this kind of nasty inequality that I'll break down in a second. So the way you can think about this inequality is, the first term is really capturing the fixed cost you have for sampling more arms. So if you operate in the base setting, there are going to be more interventions than there are in the abstract setting. So you have to do kind of more fixed exploration just to get an understanding of every single intervention in your model. So this is going to, cause you some extra regrets. But you also have the scaling cost, which is very common in algorithms like UCB, that tells you, the number of times they have to sample an arm is like proportional to the 1 over its suboptimality gap. And when you work with the imitation algorithm, what happens is some of these gap terms, these delta A's, get replaced with delta A primes get replaced with delta A. So here I should mention that A prime is an abstract intervention and A is a base abstraction. No, A prime is an abstract intervention and A is a base intervention. So if in your base model, the reward gaps are really big, but in your abstract model, the reward gaps are really small, it might actually be better for you to learn in the base model and then transfer, because basically your interventions are kind of more distinguished from each other in your base model. And this might end up helping you. Of course, you still need optimal arm preservation in this setting, right? So this is also important to note. The last thing I'll talk about is how you might transfer expectations. So you can think about, instead of transferring individual actions, just taking the summary statistics from some bandit algorithm in your base and then abstracting those mean rewards or those summary statistics and then using them to like warm start some bandit algorithm in your abstract model. So this looks something like this. You perform loads of interventions on your base model, you get some summary statistics, you abstract them, you warm start a bandit algorithm in M prime with these abstracted summary statistics. Okay, and the other thing that might be interesting to do is just, so aside from using these summary statistics to warm start your algorithm, is you might look at some of these statistics you get and think, well, maybe I don't even need to consider this intervention anymore at all. Maybe I'm happy that these summary statistics are capturing differences well enough that I can just start discarding actions. So the question is, aside from using this kind of warm start algorithm, is what arms can we eliminate straight away from these abstract summary statistics? Now, there is a kind of caveat here that we need to be able to compute alpha of the summary statistics. So you need to be able to abstract summary statistics. This might not be possible, for example, if the mean you compute isn't in the domain of your variables. But you can also always use some interpolating function of alpha that's defined over the real numbers in the case of real rewards to kind of fix this problem. And in particular, these interpolations will be quite useful for us when we're investigating how well things transfer. So if we think about what we're doing when we do this, we're applying an alpha map to an expected value, right? So as long as we can exchange alpha with the expected value, and then the average reward of the abstracted reward is kind of the same as the abstract reward, we should be fine, right? So we need to perform these two, need to show that these two approximate steps hold. Now, if you're familiar with things like Jensen's inequality, it becomes quite obvious that you need alpha to be roughly linear in order to do this exchange of expectation. The second term we'll just show, we'll find that's easily managed by the abstraction error. So one thing you might do, for example, is come up with the following bounds on the mean rewards in your abstract model based on summary statistics you get in your base. And I'll break this down in a second. So the first term is just a confidence interval. So this is just how confident you are that the mean rewards you got from your base model match the actual mean rewards of interventions. The second term is the average error of the best linear interpolation for the intervention A. So this is saying like, okay, if I take a linear interpolation of my abstraction map and I compute the average error of that interpolation over all the y values, reward values I observe in my model, how well do I fit? So this is capturing the linearity that I talked about earlier, but we need to exchange expectation and abstraction. And again, this last term here is just the abstraction error that we saw before. And this is just making sure that we can do the kind of second approximate equality. Okay, so if I call this bound kappa, kappa prime for an intervention A prime, then this kind of suggests that, a heuristic for removing arms might be if I just take action A prime, and if there's another action A prime prime such that, it's my lower confidence bound on that is higher, on the reward is higher than the upper confidence bound for A prime, then I should just stop considering A prime, right? So as long as I'm fairly confident in my summary statistics, I should eliminate good arms. Now, we don't provide a regret bound for this algorithm because there can be a lot of issues with the bias of summary statistics when you run bandit algorithms and try to estimate means from the trajectory of bandit algorithms that we don't consider. And I'd be happy to talk to people about that because I think that's quite an interesting problem. But we do have experiments in the paper that show that this performs fairly well. Right. The other difficulty with this, of course, is that kappa involves like computing this linear interpolation, which you might not be able to do at all. So we're kind of assuming that you have access to these kappas that you might not have. Now, there are some cases where kind of kappa is easy to compute. The first one is when alpha is linear. If alpha is linear, then you don't have any interpolation error. You can just use alpha directly. So this is great. So this is kind of I would say, a motivation for using linear abstractions. The other one is when you have access to action reward samples. So you have access to the trajectory. Instead of having access to the summary statistics, you just have direct access to the trajectory, the base agent in the base bandit took. And then you can just compute this, and this is kind of like moving alpha in the expectation for you. The last thing you can do is you can easily upper bound this expectation, the interpolation error, with something called a Chebyshev regression, which I won't go into. Give you just a kind of generic upper bound. So just to summarize, I mean, this work is very much preliminary, and it's kind of a call to arms. And we kind of define this framework where we think you can investigate transfer in a lot of different bandit situations. You can define a lot of interesting problems. And I think the elegant combination of a lot of approaches in bandits can solve these problems and kind of give us a lot of interesting algorithms. You know, and causal abstraction math really gives us a way to investigate these things. And I'd also stress that this work kind of tells you that IC error is not the only thing you care about, right? You care about the reward discrepancy, and you kind of care about how linear your abstraction is in some cases as well, depending on how you're transferring information across. So I think there's also a need to explore other metrics for analyzing abstractions outside of these kind of interventional consistency errors and how well these types can. Yeah, I'll stop there.
Thank you for the great talk, Nicholas. Questions, please?
Really curious on under which conditions the abstraction holds, because in the beginning of the slides, you show the treatment goes through mediator, then to the outcome, and then it can be abstracted to the treatment to the outcome. But the reason to introduce mediator is maybe there will be unobserved confounder in between the treatment to outcome. So in this case, maybe the abstraction will not hold.
Yeah, so we assume that we're just given a nice abstraction. So abstraction learning is quite difficult in practice. I don't know exactly what the effect of introducing a confounder in the mediator here would be. I mean, in this example, I'm not assuming confounding. So, but yeah, so I'm assuming in a abstraction map, you're already given an abstraction that has good abstraction error. And I would say learning an abstraction that has low error is a kind of open problem in and of itself.
Other questions for Nicholas?
Hi. Thank you for the talk. I'm wondering actually on this slide, do you require the mappings between the two SCMs to be deterministic?
Yes. But in practice, there's nothing, obviously, I haven't done the analysis, but I don't think there'll be anything stopping you from using a randomized map here. And in fact, one of our co-authors, Yorgos, has considered kind of stochastic abstraction maps. Yeah, you can learn some interesting stochastic abstractions by doing that. That would probably like kind of involve, to kind of convert this work over, would probably involve some sort of like finite sample corrections you'd have to do to account for that stochasticity, yeah.
So this means then that so all the influences on T, for instance, propagate exactly to influences on T prime.
Yeah, yeah.
And right. So
yeah.
There's yeah.
But I think you could do something like, for example, specify a distribution over alpha. So you're not, you know, and then say an expectation, maybe my abstraction error is low, and then every time step when I'm doing my bandit algorithm, I sample an abstraction from that distribution and get some sort of stochastic abstraction that way.
Next time, please again. Our next talk is via Zoom again.